Yeah, thanks a lot for having me here. Um, I'm a bit of an outsider to the field. At the same time, I'm probably the least under pressure in this community because I work in surfaces. Um, but what I want to do is, in this talk, give you a bit of a sketchy idea on like what are different challenges that you have when you calculate geochemical surface problems. The other problem that I have is I don't see what I'm doing here. Um, so we heard a lot about different scalings and so on. Typically, we work at the nano or lower scale, and we want to explain something that goes up to at least kilometers. And then in between, there is the nanoscale. The nanoscale is defined by the scale where experimentalists get nervous because it's so small, and modelers get nervous because it's so big. And I want to show you a few examples. So this is one of the problems that we want to solve with computational models. It's a mine in the Anaconda Butte complex. Just to give you an idea of the dimensions here, so this is about a mile. This is about 500 meters. They stopped pumping, or stopped mining and stopped pumping in the early 80s. Let's look how it looked in the mid-90s. And it's a great pond to do a swim, but it may be your last one because it's so rich in heavy metals, arsenic, and it has a pH of about 1.5. And then we switch to the experimental nanoscale. What are some of the minerals look like? So we use an STM. Some of you may not know what it is. Essentially, you scan a tip over the sample. You have a certain bias voltage between the tip and the sample. And then you can see surface features, or you move even more in, and you can see what is often interpreted as individual atoms, but it's essentially only sites on the surface that are either willing to give up electrons if the sample is negative, or to take on electrons. So it tells you a little bit about potential sites for oxidation and reduction. When you oxidize the sample, this Fe7S8, it starts oxidizing at these corners of these terraces that we saw before. And so now we need to understand what's going on when we do STM. And this is where the theory helps. But what you need to do is essentially combine a cluster approach with a periodic surface approach. And then you do, this is like using commercial software, for example, Gaussian. This is using commercial software, which could be anything from like Crystal, which does real 2D boundary conditions, or something like CASTEP or VASP, which does these like pseudo 3D boundary conditions where you have like a surface, surface, surface. You have vacuum gaps in between. And then you have to figure out your own software that tell you how likely it is that the electrons actually tunnel from here to there or from there to here, depending on what the bias voltage is. So what you get is not only an explanation of these experimental images, that these are not defect sites on the surface, this is just where the surface is oxidized, but also it explains why you have higher electron valence band density around these patches, why you have patches and not randomly distributed oxidation sites, and things like that. That's what we did on PBS, on pyrite, so on a number of different sulfide minerals. When you oxidize a sulfide, you not only oxidize the sulfur, but you also release a lot of heavy metals and arsenic. That's why I didn't recommend the swim in this pond. And so One idea is if you have all this arsenic released into nature, how to capture it. One idea is to build these permeable reactive barriers where you have arsenate and you want to reduce it, precipitate it. And the way to reduce it is to use a mineral that's called McKenna-White. It's FeS, and probably you feed some bacteria that keep the redox mechanism going. And what you get are funny-looking nanorods that look like this, which are arsenic sulfides of different compositions. And then the question is, are these stable forever? And do we understand what the mechanism is that they oxidize? And so we start with RealGuard, in case you don't know what it is. RealGuard is essentially ASS or AS4S4, so it doesn't have this oxygen in here. It's a molecular crystal built of these cages. And so when you try to oxidize it with oxygen, it would go in between these arsenic bonds. But it doesn't really want to go there. There are different kinetic bottlenecks that hinder it to go there. So it would start here. Is this working? Well, it would start somewhere up there, being paramagnetic. So it would come in with two unpaired spins, and it doesn't want to change its spin to become diamagnetic, which it would be here. So what we do is we just do the whole thing in water, have hydroxides, which helps with the electron transfer to this and which helps lowering this activation energy. And this is a process that is widely ignored in the geochemical community, a process that is almost ignored in the material science community. But it's extremely important because it plays a role in every corrosion process. It even plays a role in how I breathe and put my oxygen into my hemoglobin. And it governs that kinetics. Another example for a bulk process that we can model. So what we find is pyrite, so fool's gold, is one of the major hosts of real gold. However, that doesn't work unless we have a certain amount of arsenic in the system. So the more arsenic you have in the system, the more gold you can put into the system as atomic structurally bound gold. When you go higher, what you have to do is you form a separate phase, which would be gold particles, but not sort of the 1800s gold nuggets. It's more like gold nanoparticles. So we can actually find them using TEM. It's a bit of a needle in the haystack game. And so the first thing that we can do, which is relatively simple, is find like what's the incorporation or substitution energy to put gold into the structure if we have arsenic in there. And so this substitution energy is about an electron volt more energetically favorable. But then there are also, as you all know, there are specific properties that nanoparticles have. For example, as you go down with the radius, the melting point goes down. So now the question is that the same if you have the gold in a matrix or a gold that is just a free gold nanoparticle? Another thing that changes is that all of a sudden when you come to really, really, really small particles, all of a sudden it's not a metal anymore, but it has a band gap. So what do we do? First of all, unfortunately, this is already at a scale where it becomes a little difficult to do this quantum mechanically at the MD level. What I want you to see is that the faceting changes as we go up with the temperature So you have this here, and what you also see is that it starts to melt, if you want to call it melt, from the outside in. So it becomes more and more disordered as you go from the outside, and then it's completely molten. So this is an MD simulation where during the, essentially it's just one branch of a simulated annealing, if you want. This is the static image that shows it a bit better. You have a certain faceting at 600 Kelvin that becomes different at 800 Kelvin. There is still a little bit of ordering in the core, which is hard to see in this representation, in 1100 Kelvin, so that it would become completely disordered. What's the experimental picture of this? Most nanoparticles are 2 to 4 nanometers in diameter, and as you heat this up, what happens is actually that just as in the economic world, the big nanoparticles eat the small ones, so you see this one disappearing over time. And so essentially, the material scientists call this Ostwald ripening. So as you go up with the temperature from 370 degrees to about 600, from about 110 nanoparticles, you're left with 2.5. And the volume is actually preserved. However, what's going to happen is, this was our old melting curve of free nanoparticles. If you put the gold nanoparticles in pyrite, they keep growing to bigger particles before they even reach this curve. So it's essentially a solid state diffusion. And we were trying to model this. Ideally, you would like to do this at a quantum mechanical level, because there are slight oxidation state changes here. So there's some electron transfer between the nanoparticle and the matrix. We've done this so far only at the empirical force field level. And what you see is that at a higher temperature, how this particle diffuses into the matrix a lot more than at lower temperature. Another growing research field in our group is working on actinides. What we do is finding the corrosion mechanism of UO2. Essentially, you take your spent nuclear fuel, which politically correct is now called used nuclear fuel, which is supposed to indicate that you can reuse it and not just throw it out. We want to find out what is the oxidation mechanism that might take place at a place like Yucca Mountain, which may or may not be dead, which is what I was trying to indicate up there. It is officially dead, but since we don't have anything else, it may be revived. And so what's the atomic picture of this? If you were trying to oxidize something like UO2 with just dry oxygen, if it was really, really, really dry in Nevada, it would take more than 1,000 years to oxidize even one monolayer. Why? It's the same mechanism that I was trying to explain to you before. This is diamagnetic in the air. It does not want to transition. This is paramagnetic in the air. It does not want to transition to be diamagnetic unless it gets some help. And the help could be just water. But even in Nevada, it rains. Even in Nevada, the soil can be moist. And that increases the time of oxidation from about 1,000 years to about an hour. There are some intermediate steps involved that I don't want to get into. So essentially what it does, the water pushes electron density over some distance, it can be about 10 angstroms away, towards the oxygen and helps it oxidize the surface and form essentially uranium 6 plus,